Why don't I just say we know? That the orientation preserving isometries of H3 look like PSL2C. And PSL2C is just SL2C mod plus or minus I. So if you are willing to sacrifice understanding the signs, then a representation of this type is essentially a representation into the isometry group of H3. So I think he's going to tell us. Are you talking more about triangulations and things?
Yes.
Okay. So what I'm going to write down is a bit of a lie, but most. Why don't I say many? That's less committal. Many of these representations basically look like solutions to the gluing equations. So you can make this precise, but that would take a long time. So essentially, if you have these tetrahedral gluing equations, right, they tell you how you can glue, say you have the figure 8 in your two ideal tetrahedra, and you figure out these gluing equations. If you have a solution, that gives you a hyperbolic structure on your manifold, as Abhijit was talking about. Well, this hyperbolic structure, more or less, if you followed a loop in your figure 8 knot complement, then you get a loop in your two tetrahedra, right? And if those have a hyperbolic structure to them, then you can find a way so that they tessellate the hyperbolic upper half space. So then your loop unfolds into hyperbolic space. If you push it around a little bit, you can get a geodesic. That geodesic path corresponds to an element of PSL2C, basically the translation along the path. So this is very unprecise and not quite right, but this is what the correspondence is. If we spent a while, we could show this in a precise way. So if you want to think of the solutions to the gluing equations, then they correspond in a real way to representations. Now, he talked a little bit about solutions that would, in effect, collapse the tetrahedra. They're not as geometric as you would want. We all like our tetrahedra nice and three-dimensional. And so there are representations here that are quite degenerate, that definitely don't correspond in this nice way. But mostly we'll focus on ones that really do have a concrete correspondence to the gluing equations. So if you want, you can just think of all of my representations as essentially corresponding to one of his gluing solutions. Not just faithful. I'll talk a little bit about that in a few minutes. Let's see. Did I want to say something first? Okay. Yeah. So I want to spend some time just discussing some of the representations that we know, and then after I discuss these, either probably next time, then I'll talk about the set of all representations together. So well, just for fun, let's call it 0. I don't want to forget to mention the trivial representation. So we can just take trivial representation rho, everything in gamma just goes to the identity. So if I write something like this, I mean rho of gamma is the identity for all gamma and gamma. So that's not very interesting. That's why it's 0. And then the discrete faithful representation now I have to be careful, so I'm putting representations. These are any rho naught that goes to SL2C, such that if I projectivize, just meaning mod out by plus or minus 1, so P rho naught of gamma and PSL2C is a discrete subgroup, and rho as a representation is faithful. And I have no idea why representation theorists like to use the word faithful instead of injective. But they do, so we'll have to say faithful too. Okay, so as Abhijit was talking about, if I have a discrete and faithful, or sorry, a discrete subgroup of PSL2C, then I can look at the quotient by H3, and I get a hyperbolic 3-manifold. It's complete because I have because of discreteness. And if it's faithful, that means that this group is isomorphic to my fundamental group. And so by Mostow rigidity, then I know that this is isometric to my original manifold. Okay, so discrete faithful representation gives me the matrices in PSL2C that exactly correspond, since PSL2C is the isometries, they exactly correspond to the fundamental group under the isomorphism. So, question, how many do we have? So I'm just talking about representations. We actually have an infinite number of discrete faithful representations. So in the hyperbolic model, and on Monday you talked a lot about the H2 hyperbolic model and the H3, how the isometries extend. But you know that you have the, what did you call it? The triple transitivity property, where you can basically move any 3 points to any other 3 points. And in the hyperbolic plane, oh, I used the bad spot again. In the hyperbolic plane, if you take any geodesic or anything like that, since it's just a model, you can get an isometric geodesic just by essentially conjugating the model. So you know that that horosphere is geometrically identical to that horosphere. And that's essentially just, I've taken infinity and I've rotated the upper half space, so infinity landed on this point. So if you elevate this non-uniqueness condition a little bit, it corresponds to the fact that if I have manifolds H3 mod gamma 1 and H3 mod gamma 2, And if gamma 1 and gamma 2 are conjugate in PSL2C, let me call this one M1 and this one M2, then M1 and M2, they're homeomorphic and they're isometric. All you've done by conjugation is changing the fundamental domains by a maneuver something like this. So if I have one discrete faithful representation, if I conjugate it, I get another one. Okay, so I have a whole bunch of them, and there are two other slight differences that we can make a few more with. So up to conjugation, there are a finite number of our favorite representations. And I just wanted to be really clear about what these look like. Let's say we have our first one, our favorite one that we found first, rho naught. Then I could take all complex conjugates. So this means for a gamma in our fundamental group, if rho naught of gamma, it's got to be a 2 by 2 matrix, then I'm going to define rho naught bar of gamma. I'm just going to bar everything. So since the determinant is 1 and 1 is a real number, that still has determinant 1. Okay, so this corresponds to an orientation reversal. On the quotient manifold. Okay, and then you can get a finite number more from liftings. So I just want to talk a tiny bit about that. This is the probably only time I'll tell you the difference between PSL2 and SL2. So essentially, instead of looking at PSL2, which is actually a group of isometries, I said I wanted to look at SL2. And here's the cost we're going to pay. What is a lifting? So a representation rho from some group gamma to PSL2C lifts to SL2C if there exists a rho prime from gamma to SL2C such that it factors through. Okay, and it's well known what these lifts have to look like. So the obstruction for one of these lifts to exist is only 2 torsion. Because in PSL2C, there are elements of order 2. So 0 minus 1, 1, 0 has order 2. In PSL2C. But in SL2C, the element of order 2 is negative the identity, and that's central. So if this isn't central, you have nothing, you can't do this. So this is the obstruction. So if a PSL2C representation lifts, it lifts, it may have several lifts, and they differ only by sign. Okay, so there's just a finite number of them. They differ only by sign. And if you're not complement, so the number of lifts, I always forget the exact formula, is precisely measured by the Z2 cohomology. Okay, so if it's a not complement, they're just 2. Okay. All right. So now let's find some more representations. I was going to talk about reducible representations, but I think I'll talk about some other interesting irreducible representations. So a representation rho from our fundamental group into SL2C is reducible if the whole group gets sent to matrices that have an invariant one-dimensional subspace. So it's a different reducible than for varieties, but the same idea. This is a fundamentally simpler type of representation. And since you can conjugate your one-dimensional subspace to correspond with your basis vectors, they can be conjugated. So rho can be conjugated so it's upper triangular. So the whole group goes to upper triangular matrices. And if we have some time, next time I'll tell you a little bit about them, the reducible representations. So like I said before, the point of looking at a character variety is we're essentially going to look at all of the representations of our fundamental group into SL2C. So hopefully you are convinced that most of these correspond to nice triangulations, geometric structures, and the gluing that satisfy the gluing equations. And I'll try to talk next time about what looking at it from this perspective can give you. But there are a lot of interesting representations that just knowing they exist in this setting can help us see a lot of the important interactions between this perspective and the geometry. So we have the discrete faithful representation that gives us the complete structure on our manifold. And most of the solutions to the gluing equations give you hyperbolic structures that are incomplete, some of them in totally bizarre ways that are impossible for someone that's not Thurston to picture. But there are some that are incomplete in a very, very nice way. So I want to talk about them now, and we'll see that they give us parts of our variety, our representations. Yeah.
This last sentence, which representations does that apply to?
Reducible ones. Yeah. So you're reducible if and only if you can be conjugated to be upper triangular, because you take your invariant subspace, you change a basis so that it corresponds to the to your natural basis. Okay, so Dane fillings. So I'm going to start off with M, a finite volume, complete, orientable, hyperbolic 3-manifold. But to do a Dane filling, I need at least one cusp. So so I don't care if it has 10 cusps. I'm just going to focus on one of them. So my M.
How constructible is this process? From Boolean equations to representations, is it basically impossible to get the representation?
You mean from the actual gluing equation?
Someone hands you a nice triangle. Someone hands you a
Well, you'd
geometric
have to
triangle.
know where I've never tried it in practice. You'd have to know what your generators of your fundamental group look like inside your triangulations. So if you had a nice way of seeing those in your triangulations, and then you had a nice way of corresponding your solution to your gluing equation, you'd have to have a transparent mechanism so that you go through the parameters so that your solution in terms of z's and whatnot allowed you to precisely see like the triangles as a fundamental domain. Then you should be able to read off the translation that you're getting.
So like in the figure 8 knot example, you can just do it all very explicitly.
Oh, I think you can. I think it would be such a pain in the butt that you would never want to do it. But theoretically, if you can see I've never tried, if you can see the say, 2 generators of the two-bridge presentation there, then if you can pop up your ideal triangles so that they correspond to a tessellation by fundamental domains, then theoretically you can just read it off.
So it's non-trivial even for.
Well, maybe there's a fast way to do it, but I don't know of a fast way to do it. I mean, isn't this what like Zeikert does this stuff with his Ptolemy stuff? It should be secretly doing all of that. Okay, so here's my M. This is the cusp I'm considering. So a Dane filling of M is a manifold M union, let me call this cusp C. So C looks like a torus. Okay, so I lied. Here I'm considering M as S3 minus a neighborhood of the knot. So think of this as a knot complement. If you understand it for a knot complement, a more general manifold, it works the same way. If I take S3 minus a neighborhood of a knot, then M is a manifold with boundary. And the boundary, as Abhijit said, is this cusp that you truncate, so the boundary looks like a torus. Okay, so I'm going to take my manifold with torus boundary and union along the boundary S, which is a solid torus. Okay, so I'm going to identify the torus boundary of the solid torus with this by homeomorphism. So I glue M to S by identifying by homeomorphism of, what did I call my cusp again? C? C to the boundary of S. Now you can do this in many ways. There's an obvious way, just plunk it in like that, but there are lots and lots of other homeomorphisms. To do the construction properly takes a fair bit of time though, so I'm just asking you to believe me that there are lots and lots of different homeomorphisms. And basically, the homeomorphisms are determined by where a meridian goes in this torus. So for any different loop class in this torus, you get at least possibly a different manifold. So on the level of fundamental groups, I just want to talk about what the fundamental group of my Dane-filled manifold would look like. So if we use Van Kampen's theorem, it'll be pi1 of m, free product, pi1 of my solid torus, minus, and then if you remember, you minus mod, then you have to track where the generators of the torus go, the boundary. So if I look at meridian and longitude here, well, let's call this T the generator for my solid torus. The meridian here is going to get killed. The longitude doesn't. So the longitude gets glued to something over here. So I get something that looks like T equals a word in pi1 of m, right? This loop gets identified over here. It becomes a loop there. And this meridian loop on the right side is trivial. And on the left side is some product of longitudes and meridians here. So I get 1 equals, say, mu to the A, lambda to the B, where mu lambda are meridian and longitude of the cusp in M. So what this means is that this pi1 of S is just the cyclic group generated by T. That means this is isomorphic. Since I've introduced a T and now written a T in terms of other generators in here, I don't need my T anymore. So it's just isomorphic to pi1 of M mod this relation. So it's a quotient. There is, but you have to be careful and in the interest of time. It's essentially, you argue that any homeomorphism, up to homeomorphism, that this identification just depends on where this meridian goes, and then you can homotop it on the torus so that it looks like A powers of mu, B powers of lambda, or something like that. I might have the sign wrong. So you're identifying this torus boundary with this torus boundary, and if you push mu a little bit, just deform it, then you can see this curve is going to essentially, because the fundamental group of C is just the abelian group generated by mu and lambda, then any curve here looks like a power of mu times a power of lambda. So that A and B are essentially which powers of mu and lambda this curve gets taken to. In terms of pi1 of M, it depends on the situation. So if you have a knot complement, the Werdinger presentation will give you a mu. You can choose a base point, pick your favorite. And then there are ways to algorithmically read off lambda in terms of the Werdinger representation. Like Ilya was saying, you can draw the blackboard of the knot, and you could do it by hand by pushing off lambda and then seeing how many times you sort of wrap around. For certain classes of knots, there are nice formulas for writing lambda too. Okay, so we get a bunch of quotients, and Thurston Abhijit, I think, is going to talk about this more in depth, so I'm just going to state the result. So he proved that if M is hyperbolic, then all but finitely many Dane fillings so if we do this, then for this A and B, we often call the Dane-filled manifold the thing I wrote as M union over S. Oh, I wrote it wrong. We glued along the cusp S. Oh no, I forgot to look up if it's A over B or B over A. I might be totally backwards. We use this notation to reflect the A and the B. So they're all but finitely many Dane fillings MA over B. So notice that you can think about this A over B. So A over B, usually you'd think of it as a rational number, but if you divide by 0, it also corresponds to an OK gluing association.
If you do zero surgery on the unknown, it's 2 cross S1. Does that resolve A and B?
I'll let you figure that out because there's no way I can do that at the blackboard. So I might have, it could be B over A. I forgot to look it up. There's a standard way to do that. So we started with a hyperbolic manifold, and now I have infinitely many other related hyperbolic manifolds. So if you look at the group theory, can I associate representations between these two? So in general, if I have, let's say, phi, so in this situation, I have a surjective homomorphism from pi1 of M to pi1 of the A over B, or B over A's. So in general, if I have a surjection, then we can see representations of the smaller group, if you will. Let me say this better. If I have a surjection from gamma 1 to gamma 2, representations from gamma 2 to SL2C give representations of gamma 1 to SL2C, right? Because all I have to do is take gamma 1 to gamma 2 by my surjection, and then I can define gamma followed by rho.
You don't need it to be a surjection.
I don't need it to be a surjection. So I'll say it like this. If I have this, I can always do that. If phi is a surjection, so I forgot what I was going to say. Right, if phi surjects, so if phi is, say, in something silly like the trivial representation, then a lot of the rows from gamma 2, okay, if phi is a trivial representation, takes everything, or trivial map, takes everything to the identity, then this looks the same for every single representation gamma 2 might have. But if it's a surjection, then this looks different for every different row I have. So if phi is a surjection, then the phi the compositions that you get are all unique. So what I mean is, if I'll say it explicitly. If I have rho and rho prime both from gamma 2 to SL2C, then phi of rho different functions, then phi of rho and phi of rho prime are also different. Right? Because you're seeing that being rho and rho prime being different means that there's some element gamma here that gets sent to different image under phi and under rho and rho prime. So since I've surjected the composition, I get different targets too. All right, let's see. Okay, so we can conclude that if M has at least one cusp, then even up to conjugation, there are infinitely many representations of pi 1 of M to SL2C that are let me see, sorry, that factor through Dane fillings. Right? So to be a little bit more precise, I keep wanting to write over there. We know from the theorem that I made no attempt at proving that all but a finite number of Dane fillings are hyperbolic. That means that if A over B is a hyperbolic Dane filling, it has a discrete faithful representation of its own into SL2C, right? Because it's a hyperbolic manifold. So it has a discrete faithful representation. Let's say rho A over B from pi 1 of M A over B to SL2C. And this gives us a compound representation where I start with pi 1 of M, and this being that surjection map to SL2C. And so what group, so that's my representation, and when I put in my fundamental group of my original manifold, this is just isomorphic to pi 1 M A over B, right? Because this is a discrete and faithful representation. So the image of this representation is isomorphic to this fundamental group. So I have all these representations where I basically just take my manifold, surject the fundamental group onto the fundamental group of the Dane filling. If they're infinite, all but finitely many of those are hyperbolic. So I take that fundamental group, realize it as matrices in SL2C, and so I get lots of representations whose images are discrete. They correspond to a hyperbolic structure, but just not the hyperbolic structure of M. They correspond to the hyperbolic structure of the filled manifold. So we have a wealth of representations that correspond to totally natural hyperbolic geometry. And let me just finish by attempting to draw the figure 8 and just explain a little bit more what it looks like. Under, over, under. Over. It's a bit of a pointy figure 8. Okay, so our original manifold, let's say M is S3 minus a tubular neighborhood of K. K is my figure 8 knot. So my manifold is S3 minus this. Okay, and I hope that looks right. Okay, so there's a natural hyperbolic structure on this. As we talked about, that gives us essentially 4 representations. The natural structure, reverse orientation, up to sign. Okay, now I told you that I can Dane fill this, and all but finitely many of my choices give me a hyperbolic manifold. My choices are indexed by where the meridian goes in the fundamental group of this torus. So I have essentially a Q union infinity's worth of torus, of choices. So I can essentially glue the torus back in, and I fill this up, and I get a closed 3 manifold. And Thurston's theorem says that for all but a finite number of those possibilities, that closed manifold is hyperbolic. So what is the geometry looking like? Imagine I've filled it in with my favorite A over B. So now I have M A over B, and I chose a hyperbolic filling. So now I have a hyperbolic structure on the entire thing, including the knot part. So what are these? How are these really relating to the original manifold? Well, imagine that you have some triangulation in hyperbolic space, fundamental domain for this. Well, how do I get a fundamental domain that's telling me a hyperbolic structure for my original manifold? Well, I just take the fundamental domain for this closed thing, and I erase whatever goes to the thing I filled in. Does that make sense? So this is a closed manifold now, and my closed manifold's hyperbolic. So it has, let's say I triangulate it with hyperbolic triangles, tetrahedra, because it's 3 dimensions. And those, I've chosen them nicely, so there's a nice tessellation of the hyperbolic half space by that. Well, that gives me a geometry on my original manifold, because if this is one of my hyperbolic tetrahedra, which I can't draw, that corresponds to this, maybe this part covered the part of the knot. So I just erase that. If I erase all lifts of where the knot came from, then I get a hyperbolic structure on my knot, except I've got little tubes missing, right? Which means that the hyperbolic structure on my knot complement's not complete. So if I have a little tube, then I can get a Cauchy sequence that doesn't converge. So the hyperbolic structures on the knot complement give me incomplete hyperbolic structures on M. So the representations coming from here give me representations coming from here that are nice hyperbolic, correspond to hyperbolic structures, but they're all incomplete structures. And just a word about how many you get. If this is closed, then by Mostow rigidity, there's always one discrete faithful representation up to orientation reversal and signs. So for this, you'll at least get something like 4 or 2 in here. So you get a finite number of these complete structures from here, but in certain situations, you could get a lot of more structures from here if, say, M itself had 2 cusps, and you only filled one of them. We'll talk about dimension next time, and you can see a lot more. But these are where basically all of the representations most of the representations that we know of are just these. There are a couple of more very special kinds that we also know of. But essentially, and again, I'll talk about dimension, for the figure 8 knot, we have an uncountably infinite number of representations, even up to conjugation. Okay, and I've told you countably many, and the other ones are basically mysterious. And so the idea is, let's look at all of the mysterious ones together with the ones that we know, and as a set together, actually they tell us more powerful things than trying to understand them one by one. Sorry I went over.